All right. Let's do a few things. We'll jump back into limits in a minute here, but a couple people asked me if I could talk about tangent lines for just a moment. So let's do a tangent line example. Let's find the equation of the line tangent to f of x equal to, let's go that way, 3 minus x squared at the point, let's go 4 comma negative. So there's the setup. I'm trying to find the equation of tangent line. Really, the harder part of this, well, I should say, whenever you're finding the equation of a line, you need two pieces of information. You need a slope and a point. We have a point. So we need a slope and a point. But we already have the point. It's right there. So all we really need is the slope of the tangent line. And here's the idea, which is really, so these questions, the questions like this on some people's homework assignments, are really kind of meant as an entry into where we're eventually going to end up, which is finding the slope of the tangent line using the limit definition of the field. That's eventually where this is going to, but that's not what we're going to do. Well, it is what we're going to do now. We're just not going to use all those words. So let's draw a picture. Let's draw this function, 3 minus x squared, which looks about like this. And even though I haven't done an excellent job of drawing, let's pretend like my point is right here to give myself a little bit of room to work with. That's 4 comma negative 13. And the idea is I want to find the slope of the tangent line. But what I'm actually going to do first is I'm going to find the slope of a secant line. So I'm going to say, let's pick another point over here. And I've gone over a little bit. I've gone over h. So this point here, or this x value here, is 4. And this corresponding x value here is 4 plus h. Just a little, so the reason I'm using h instead of like a number is because I want to be able to let h be really as small as I want it to be. So we want to find the slope between these 2 points, 4 comma negative 13 and 4 plus h comma, whatever the y value is. Well, I can find the y value by plugging in 4 plus h into my function. So I'm going to say f of 4 plus h. That's the line. Oh, I'm so excited. I have this tiny little ruler that I keep remembering to bring. I can draw straight lines with it. I know it doesn't sound like a huge deal, but it's like, I'm not great at drawing straight lines, but it came with a ruler. So the idea here is I'm trying to find the slope of this secant line, which I know because of how my picture looks, it looks kind of like a tangent line, but that, right. So we can emphasize the fact that this kind of goes around it like that. So what we're going to do is we're going to find the slope of that secant line, and then we're going to let h get really, really small. Because if h gets smaller and smaller and smaller, the secant line gets closer and closer and closer to being the tangent line. Like instead of if my point's right here, then my secant line's like that. And if my point's right here, my secant line's like that. And eventually I get closer and closer to finding the actual slope of the tangent line. So that's all we're going to do. We're first going to find the slope between 2 points on the graph, 4 comma negative 13 and 4 plus h comma f of 4 plus h. Just to make writing it not too terrible. Well, we know how to find the slope between 2 points, or we probably have at some point in our past, we might have forgotten. I'll remind you, the slope between 2 points is just the difference in the y over the difference in the x's. So the slope between these 2 points is, you can write it as the change in y over the change in x, or y2 minus y1 over x2 minus x1. In this particular example, it's going to be, we can subtract in whatever order we want. Typically, we are going to write these things first just because it's easier to write it that way. So I'm going to write this as f of 4 plus h minus negative 13 over 4 plus h minus 4. Great. And then we're going to do all the algebra we need to make this as simple as possible. So let's go ahead and simplify this. I'm going to run out of room. I'm going to need a piece of paper. Oh, well, happens. So f of 4 plus h is just going to be 3 minus 4 plus h quantity squared, minus 13 is plus 13. And then 4 plus h minus 4 is just h. Right? The 4 is canceled? Yeah. And then we're going to multiply that out. So running out of room. Always running out of room. My biggest, not my biggest failing in this class, but it's a failing I have. Sure. So simplifying this, we get 3 minus, let's see, 4 plus h squared is 16 plus 8h plus h squared plus 13 all over h. Doing a little more simplifying, 13 plus 3 is 16, 16 minus 16, those cancel out. So I'm really just left with 8h plus h squared over h. And then if I cancel the h's, or really I guess I could factor out an h from the top and then cancel some h's. I'm left with 8 plus h. Which seems like I made a mistake. You guys let me get away with it. I was working too fast though. It was easy for you to let me get away with the garbage I just wrote down. I did something that was, well, I forgot something. I forgot about that minus sign. Now, let me actually, here's a better question. How do I know I made a mistake? Well, this slope here, unless h is really super negative, this slope is positive. But my tangent line or my secant line looks like it has what kind of slope? Definitely negative. That's how I saw right away. Oh, I made an error somewhere. So I should go back and be like, this should actually have been a negative 8h and a minus h squared. Sorry about that. And then this should be a h times a negative 8 minus h. That's terrible. I hate doing that. This would be a negative 8 minus 8. Terrible. All right, so the slope of that secant line is negative 8 plus h. Okay. Oh, thank you. Yeah, gosh. Jeez. Terrible. Thank you. So the slope of the secant line is negative 8 minus h. And now here's the idea. We're taking this, I'm going to draw it again. Right, we've got, there's our point that we're interested in the tangent line. So what we really want is, oh, I got all the colors today. Yeah, cool. It's green. Where's green? Okay. Yellow is green, sure, why not? So there's my tangent line. That's the line we really want to find the slope of. Oops, you can't see that. So what we're doing is we're taking this secant line between our point that we want, 4 comma negative 13, and this other point over here, 4 plus h comma f of 4 plus h. And we're letting this point get closer and closer and closer and closer and closer to that point. So that the tangent line, the secant line slope becomes closer and closer and closer to the slope of the tangent line. And the way we're going to achieve that is by letting h get smaller and smaller and smaller. Because we want that point to get close to that point. Well, they only differ by h. So we're going to let h go to 0. In other words, to find the slope of the tangent line, we're going to take the limit as h goes to 0 of the thing we calculated, of f of 4 plus h minus f of 4 all over 4 plus h minus 4. Which we did all the work already. Right, that's what we were calculating up here, f of 4 plus h minus f of 4 all over 4 plus h minus 4. And that ended up being equal to minus 8 minus h. So really that's going to be the limit as h goes to 0 of minus 8 minus h, and the h goes to 0, so we're left with negative 8. And that is the slope of our tangent line.
So the secant line is basically just the slope. How do we define the secant line?
So the secant line is a line that goes through 2 different points on the graph.
Just the slope.
Well, we're finding the slope of that line.
So the secant line is basically the line that connects any 2 points, and therefore is equal to the slope from it's equal to the change in y over change in x from point A to point B.
Well, I would say, sure, the slope of that line is equal to that. The secant line itself is just a line, right? And then what we are looking at is the slope of that secant line.
I don't think I'm understanding how they differ.
Well, a line is more than just its slope. Right? There are lots of different lines that have the same slope. And but a line is an equation, a line is a set of points, all, satisfying this equation. And yes, we talk about the slope of a line, but a line has more features than just its slope.
So basically, the secant line is a line that has the same slope as our graph has from point A to B.
Yes.
Okay, that makes sense.
Yeah.
Okay, so just to clarify, I'm getting all parts of this right. If we're asked to find the line tangent to a given function, we would take advantage of using the secant line through a given point to another point.
Yeah. So here's the idea. Eventually, we're not going to do it this way. This is kind of how they're building up towards talking about what a derivative is. But the idea is really, if someone in the future said, find the equation of the tangent line at this point, you'd be like, oh, I'm going to take the derivative of the function, plug in the x value that they've given me to find the slope of the tangent line at that point, and then find the equation of the line. But the whole idea behind this is that we're really using this example not because we care about finding the equation of the tangent line. We care about finding the slope of the tangent line and talking about how we do that. And the whole idea with derivatives is that the way we find this slope of the tangent line is by first finding the slope of the secant line and then letting that second point travel closer and closer and closer and closer to that first point, so that the slope of your secant line approaches the slope of your tangent line. That's what we're doing here. So here, the slope of this tangent line is -8.
So I remember going over this in lecture.
Mhm.
So from here, we would just basically have hypothetical h values, and we to try to get closer and closer. And once the values stop differing from each other,
Right.
that's when we find what that slope.
Exactly. So you could totally have done this in a kind of more complicated way and said, I'm going to take, this expression, 3 minus 4 plus h squared plus 13 all over h, and plugged in smaller and smaller values of h and gotten values that were closer and closer and closer to 8, or sorry, -8, apologies. So for example, if we made a little table, I will just point out, here's h and here's the slope of the secant line.
But you're not saying there.
Thank you. So if I picked an h value, like 1, the slope of my secant line would have been -9. And if I picked a value a little smaller, like 0.5, I would have had -8.5. And 0.1, -8.1. And 0.01, right? We were getting closer and closer and closer to -8.
Class is the longer form way of, instead of applying what we know about limits, we would have.
Right, you're making like a table, right? Yeah, which actually we're going to see an example just in a little bit here. But yeah, that is sometimes we can't do this algebraic manipulation. There are some functions that don't lend themselves very well to this at all, and so we do make a table and kind of ask ourselves what's going on there. Yeah.
So the tangent and the secant line, their name doesn't really do with trigonometry, right?
I mean, yes and no, but for now, not in any way that's meaningful to us at this moment. So here we can now, so we've done the hard part. We found the slope of the tangent line. The rest of it is the kind of just, we have to make sure we answer the question that was asked. So to find the equation of this tangent line, I like to use the point slope form, and say y minus my y coordinate, which was -13, equals my slope times x minus my x coordinate, which was +4. And then you can go ahead and isolate y if you like. I've got y plus 13 equals -8x plus 32, and then subtract 13 from both sides. Y equals -8x plus 19. But again, that's not what's the hard part of this question. The hard part was finding the slope of the tangent line. This is supposed to be the relatively straightforward part after that. Sometimes they'll ask you just for the slope of the tangent line. Sometimes they'll ask you for the equation of the tangent line. So make sure you are reading the question, whatever question is being asked carefully to know what you're supposed to be trying to answer. Other questions about this one before we do some more limits? Yeah.
So In my discussion the other day, like my TA did it away,
Mhm.
kind of like flipping them. So like he did where he used like X.
Instead of using like the number that you're finding the slope of the tangent line at.
I mean, I think so.
So let's do one more example because this is again, this is where it's all leading towards eventually. So let me ask another question that's similar but a little bit different. Let's say we want to find, we'll do slope this time. We just want to find the slope of the line. Picking some easily algebraically manipulated examples here. Line tangent to f of x equal to 2x squared minus 6x plus 1 at x equal to, let me see here, let's make it not terrible, James. Yeah, let's say x equal to 3. Sorry, I should not use x equal to 3. I should probably use a equal to 3 because that's kind of typically how it's done when they pick a specific value. So there's two ways we can do this. One way is the way that's more work generally. So method 1 would be to find the slope of the tangent line at that point. So I'm going to draw a picture again. Sure, pictures are great. Here's my parabola opening upwards. And here's the point where a is equal to 3. So here's 3 comma f of 3. And I can do the same thing I did before, meaning I can find the slope between this point and some other point h away. So the slope of this secant line is just the slope between this point and the point 3 plus h comma f of 3 plus h. You can see that well. Let's zoom in a little bit. So method 1, the slope of the secant is f of 3 plus h minus f of 3 all over 3 plus h minus 3. The bottom all is going to simplify to h. And then the way we find the slope of the tangent is by finding the limit as h goes to 0 of f of 3 plus h minus f of 3 all over h. I simplified the bottom. Or the other way one could do this is by finding. So this is the slope of the tangent at a equal to 3. The other way people do this, which is the way we're going to do it eventually, is by finding the slope of the tangent at any value x. So the slope of the tangent at any x is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h, and then plug in 3 for x. That's kind of, I think that's the difference we're talking about.
Yeah, he used like f of x prime minus f of x over x prime minus x.
Oh, he's x prime. Okay, that's fine. Oh, that's so that is the algebraically less nice way of doing it, but it's also a technically correct way of doing it. So there are lots of ways of doing this. Yeah.
So what is a like this point relative to the graph? Because earlier it made sense, but now when it's a, it's like
So a is 3 here.
right. So like, what are we using that for? It made so much more sense when it was like a point that we were using into the equation earlier.
Well, it still is. So here our point is 3 comma, if I plug in 3, I get 2 times 9, which is 18 minus 18 plus 1.
Oh, okay.
So my point is 3 comma 1.
Okay.
So let's talk about the two ways we can do this. Maybe we'll talk about the third way is not as nice. I promise you. So doing it this way, if I find the limit, doing it this way, I should say, because I really got to do past this. The limit as h goes to 0. So f of 3 plus h, okay, I have to plug in 3 plus h to my not very lovely function here. I'm going to get 2 times 3 plus h squared minus 6 times 3 plus h plus 1 minus f of 3, which we just said f of 3 was 18 minus 18 plus 1. over 3 plus h minus h, which is h. Okay, so then when we do this, here's what we get. So simplifying this, and again, this is just a lot of algebra. 3 plus h squared is 9 plus 6h plus h squared minus 18 minus 6h. The ones cancel. Now here's what you should expect to happen every time you do this kind of thing. You should expect eventually everything that doesn't have an h in the numerator to cancel out. So then you can factor out an h from what's remaining and cancel it with one of the h in the bottom. Because that h in the bottom is the problem, right? Looking at this limit as is, it's a 0 over 0 type of limit. And that's a problem, right? We have to be able to do some algebra to simplify it. So here, the limit as h goes to 0. Let's see, I'm getting 18 plus 12h plus 2h squared minus 18 minus 6h over h. The 18s cancel. So I'm left with the limit as h goes to 0. Let's see, 12h minus 6h is 6h plus 2h squared all over h. And you can either divide each thing by h or factor out an h and cancel it. I'll do the dividing way this time. So divide each thing by h, you get 6 plus 2h. And then we can finally take the limit. You get 6 plus 2 times 0, which is 6. So the slope of the tangent line to this function at that one particular point is 6. And then if I ask you what's the slope of the tangent line at when a is equal to 4, you'd have to do all this work again. But plug in 4 for a instead of 3 for a, which is kind of annoying. So instead, what we end up eventually doing is saying, well, I don't want to have to do that 5 different times. I want to find 5 different tangent lines. So what we're going to do is make it general. We're going to say instead, we're going to look at this kind of expression. So we're going to look at the limit as h goes to 0 of, instead of f of, so this here, I'll just remind you, this was the limit as h goes to 0 of f of 3 plus h minus f of 3 all over 3 plus h minus 3. Now we're going to use a variable instead of the constant 3. By the way, in case I haven't said it already, this expression, those are both called the difference quotient. It's just the change in the y over the change in the x. It's the slope of a line between 2 points, but it's often called the difference quotient because literally it's a quotient, right, a fraction of differences. That's why it's called that. So here things are maybe not as nice. So we're looking back at our function. Remind ourselves the function is 2x squared minus 6x plus 1. So we're just subbing in x plus h for each x. So we're getting the limit as h goes to 0 of 2 times x plus h squared minus 6 times x plus h plus 1 minus f of x, which is 2x squared minus 6x plus 1 all over x plus h minus x is just h. The same kind of thing is going to happen that already happened before, in that we're still expecting the not h things in the numerator to cancel out and be left with only h's in the numerator, so then we can factor one out and cancel the h in the bottom. That's still the process that we're hoping is going to happen. It's always what we're expecting to happen with these kind of problems. So doing it this way, we get the limit as h goes to 0. Okay, 2 times x squared plus 2xh plus h squared minus 6x minus 6h plus 1 minus 2x squared plus 6x minus 1 all over h. The 6x's cancel, the 1's cancel. The minus 2x squared will eventually cancel after I distribute this 2. I get the limit as h goes to 0 of 2x squared plus 4xh plus 2h squared minus 6h minus 2x squared all over h. Now this 2x squared cancels with the minus 2x squared, and we're left with the limit as h goes to 0 of 4xh plus 2h squared minus 6h h. Divide each thing by h, and you're left with limit as h goes to 0 of 4x plus 2h minus 6. Plug in 0. Plug in 0 for h. You get 4x plus 0 minus 6. So that's the slope of the tangent line for any value of x. And then we want to know what the slope of the tangent line is specifically at 3. So plug in x equal to 3, and we're going to get a slope of 4 times 3 minus 6, which is 12 minus 6, which is 6, just like we got there. So this way of doing it is what we're eventually going to be doing more often. But the idea is you can use this to find the slope of the tangent line at any point on the graph, as opposed to one particular point on the graph. So hopefully that kind of addresses what you're asking. I know I didn't probably do it the same way that was done in your class, because they're using the slightly, in my opinion, more terrible version of this definition, because it's a little less computationally nice. Yeah.
So what is the other version? Because I've never seen it on any other way.
So the other version, which actually I'm going to hold off on that. We will get back to that once we start talking about the limit definition of the derivative. I will point out that the other version is to say that you can find the slope of the tangent line at x equal to a by finding the limit as x approaches a of f of x minus f of a, all over x minus a. Same idea, just a different way of saying it.
I think I missed it, but after you look towards, how do you get from like the limit as h approaches 0 for f of x? How'd you get to the next one?
So that step there. So those numbers came from the function that we're using. So the function that we were talking about has for this whole problem has been 2x squared minus 6x plus 1. So all I did to get from sorry, someone still. All I did to get from here to here was I said, okay, well, come on, is that f of x plus h is just 2 times x plus h squared minus 6 times x plus h. And then subtracted f of x. Other questions? Yeah.
So the main difference between the two is that in the first method, you just right off the bat, you plug in the x value.
Right, the actual numerical value.
And so then you write, so then you solve all of that,
Mhm.
and then you write the limit, then you write the whole thing.
Right,
In the second one, you just don't plug it in and solve it all out first.
right, exactly. And eventually we will move towards the second one when we talk about the limit definition of the derivative. But let's move back. So that's why they're talking about the slope of the tangent line so early on, is because they're trying to get you thinking about the fact that we're going to be doing this very soon in chapter 2 somewhere. Well, let's go ahead and move back a little bit and talk a little bit more about these 0 over 0 limits, because we definitely want to finish talking about those and then start talking about the precise definition of the limit, which is probably no one's favorite, but is something we do need to cover. So let's look at a few more 0 over 0 limits, like the limit as x approaches pi over 2 what do we got here? 1 minus sine of x cosine of x. Trig. So let's see. If we are trying to evaluate this, if we plug in pi over 2, I'm going to get 1 minus sine of pi over 2 cosine of pi over 2. And that's going to be sine of pi over 2 is 1, cosine of pi over 2 is 0. So it is a 0 over 0. So we do have to use something, right? We have to do something here. And I will say with the trigonometry examples, there's not as much wiggle room. When we're dealing with trig, one of the few things we have is some trig identities. So often if you have a 1 minus sine or a 1 plus sine or a 1 plus cosine or a 1 minus cosine, any of those 4 things, it often is very beneficial to multiply by the conjugate, because multiplying by the conjugate will end up getting you to a trigonometric identity. Let me show you. I'm going to multiply this by 1 plus sine of x over what? Right. Just want to make sure everyone's with me there. Okay, cool. So then, as is with other conjugates, like when we had the square root conjugates last class, we multiply out the things that are conjugate and not the things that aren't. So the denominator, I'm just going to leave as is. I'm going to leave it as cosine of x times the quantity 1 plus sine of x. It's not going to do me any good to distribute that cosine and get cosine x plus cosine x times sine of x. I could, it's not useful. On the other hand, I definitely do want to multiply out 1 minus sine x times 1 plus sine x. So I'm going to get 1 times 1. The middle terms cancel, right? I get 1 times sine plus negative sine times 1. That's sine minus sine, that goes away. And then finally I get minus sine times plus sine, which is negative sine squared of x. And the numerator is a trigonometric identity. So I'll remind everybody of everyone's favorite trig identity. Sine squared theta plus cosine squared theta equals 1. Or whatever you want to use as your input. You can use x, you can use y, it doesn't matter. But the point here is that if I isolate cosine squared theta is equal to 1 minus sine squared theta. Question? You should definitely, so, I mean, that's a big question because there's a lot of trig identities, but I would say you definitely want to know this one. And in this class, for now, I would say you want to know this one. You probably want to know that sine of 2 theta is equal to 2 sine theta cosine theta. And there's some other ones that come up, but really not until 21B. So yeah.
So I did make a list of all the ones that are going to come up at this in 21A.
Okay.
So you guys can get a picture, post my calendar.
Totally, yeah. Well, you can, if you want to take a picture, you can send it to me and then I can post it on camera.
I'll do that.
Awesome. Thank you. Very helpful. All right. But for now, I would say that these are the ones that I'm thinking of that come up most readily. So simplifying this, we've got the limit x approaches pi over 2 of cosine squared x over cosine x times 1 plus sine of x. And now we can cancel one of those cosines. So you cancel a cosine here and a cosine here. I'm left with the limit as x approaches pi over 2 of cosine of x over 1 plus sine of x. And now we can plug in pi over 2. So plugging pi over 2, I get cosine of pi over 2 over 1 plus sine of pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Like 0 divided by 2, which is 0. So sometimes the trigonometry, I would keep in mind this specific kind of thing is that often if you see 1 minus sine, 1 plus sine, 1 minus cosine, 1 plus cosine, multiplying by its conjugate is usually the right thing to do. Okay. A few more examples. Yeah, okay, sure. We did that one. Sorry, one sec. Oh yeah, a couple other things. So sometimes, okay, come on, papers. Sometimes algebra doesn't really get us what we need, though. Sometimes you might have something like a limit as x approaches 4 of the absolute value of 2x minus 8 over x minus 4. Absolute values are kind of a pain. So here's the thing we have to know about the absolute value. The absolute value is really a piecewise function. The absolute value of some stuff is equal to, well, if the stuff is already positive, you just leave it alone, right? The absolute value of something positive is just whatever you got. On the other hand, if the inside stuff is negative, the way we turn that negative into a positive is by multiplying by -1. So if the stuff is negative, you really want the negative of that negative stuff. Yeah.
And we put 0 as part of the positive.
Either way, we put it wherever we want to. We put it there or there. Yeah.
Go back to the other sheet of paper. real quick.
Yes.
Thank you.
Cool. Also, yeah, I can't help myself. I have to say this. So just so you all are aware, the square root of x squared isn't x. It's x sometimes, but it's negative x sometimes. The square root of x squared is the absolute value of x. Here's how I always see it. What's the square root of 5 squared? Right, it seems like a dumb question. Bear with me. It's 5, right? Square root of 25, which is 5. What's the square root of -5 squared? Also 5. So, right, it does the same thing as an absolute value. An absolute value takes an input of 5, gives you back 5, takes an input of -5, gives you back positive 5. So really, when you see the square root of x squared, it is important to recognize that a lot of the time it's not, it's just going to be x, but really the broader picture is that it's the absolute value of x. So it seems like a good place to say it. So I said, okay. So to deal with this, well, we've got different things going on either side of 4, right? If x is bigger than 4, if x is bigger than 4, then 2x minus 8 is going to be a little bit positive. So the absolute value of 2x minus 8 is just 2x minus 8. So I can rewrite this as the limit as x approaches 4 from the right of just 2x minus 8 over x minus 4. Because the inside stuff was positive. And then I can simplify. That's the limit as x approaches 4 from the right of 2 times x minus 4 over x minus 4. The x minus 4's cancel. And have the limit as x approaches 4 from the right of 2. What's the limit as x approaches 4 from the right of 2? Well, there's nowhere for x to go, right? The function is just 2. 2 the whole way, so we just get 2. It feels kind of silly because you're asking the question, what is the function getting closer and closer to as x is closer and closer to 4? But the function is just 2 the whole way. So it's 2, 2, 2, 2, 2. So it's getting closer to 2, but it was kind of already there.
That means if you graph the original function.
We'll graph it in a second. So let's look at the limit from the left-hand side. As x approaches 4 from the left. Okay, well, if x is approaching 4 from the left. Oh, yeah, question. Well, so what I did was I factored out a 2. So if I distribute this 2 back through, 2 times x is 2x, 2 times -4 is -8. Okay, so then if we're approaching 4 from the left side, the less than side of 4, 2 times a number a little less than 4 is less than 8, minus 8 is a little negative. So here, when I take the absolute value of 2x minus 8, I have to rewrite this as limit as x approaches 4 from the left of -2x minus 8 to ensure that that result in the numerator is positive. Right, like, let's pretend x was 3. What's 2 times 3 minus 8? -2. But I don't want the opposite value of 2 times 3 minus 8 to be -2. I want it to be +2. So, right, the absolute value of 2 times 3 minus 8 is -2 times 3 minus 8. So I'm taking that negative inside and making it positive. If this seems a little weird, remind you what the absolute value function looks like. Right, everyone agrees, like that's what the absolute value function looks like. Oh, but look, this is the piecewise function. Y equals x if x is positive, and this line here is y equals -x if x is on the left side. That's all we're doing is we're taking our input that we know happens to be a negative number and saying we need the negative of that to turn into a positive number. So here, the absolute value of 2x minus 8 is -2x minus 8 because the insides are negative. And then we can still factor out, I guess I would factor out a 2 still, limit as x approaches 4 from the left of -2 times x minus 4 over x minus 4. The x minus 4's cancel, and you get the limit as x approaches 4 from the left of -2, which is -2. So, limit from the right is 2, from the left is -2, which means the overall limit.
Is it x minus 4 or is it x plus 4 because it's the -8?
Sorry, say it one more time.
When you factor it, is it -2 times x minus 4?
It is. Because so what I have the negative out in front there, and then from the 2x minus 8, I'm still factoring out a positive 2. So I'm pulling out the 2, I'm getting -2, and then it's still left with an x minus 4 there. graphically, here's what this looks like. So to the right of 4, the function is just always 2. Pick any value bigger than 4. 5, 6, 7, 8, 9, pi squared, right? Any number you pick, if you plug in a number bigger than 4 into this, you're going to end up getting 2. No matter what you pick. Do it real quick. Pick 5, pick 6, pick 7. Plug it in the top. Let's see. 7 is 14, 14 minus 8 is 6. And then 7 minus 4 is 3, and 6 divided by 8 is 2. And it worked for your number 2. Because really, whatever you get, it's always going to be positive. On the other side, if you pick a number less than 4, like 3 or 2 or 1 or 0 and plug it in, the top is still going to be positive. It has to be, because it's an absolute value, but the bottom is going to be negative. You're going to get negative 2 out. So on the left side of 4, this function looks like this. And so we have this function approaching 2 different values from the left and the right side of 4, meaning the limit of 4 doesn't exist. Yeah.
Could we factor the 2 from the beginning when we have the function?
Totally. Yep. You can definitely write the absolute value of 2x minus 8 as the absolute value of 2 times x minus 4, which is 2 times the absolute value of x minus 4. Oh, sorry. Yeah. Sorry. I'm zooming in too much. Yeah.
So as long as the constant is positive, we can just factor.
You can even factor out if it's negative. So just so you can also, like, for example, if you're dealing with the absolute value of, like, say, negative 3x plus 12, and I want to factor out the negative 3, I can. It's the absolute value of negative 3 times x minus 4. And then when you have an absolute value of a product, there is a rule for absolute values of products. You can say it's the absolute value of negative 3 times the absolute value of x minus 4. And then the absolute value of negative 3 is just 3. So that's how you deal with something like that. You can always factor constants out of opposite values. You have to make sure that if they're negative, they eventually come out as a positive.
So another question is what you were saying earlier about the square root. So you said the square root of 25 is 5, but also it can be negative 5.
No, I did not say that.
Am I, what are the misunderstanding?
So the square root of 25 is always 5.
But shouldn't it also be negative 5?
No, it should not, because we want the square root to be a function. And functions take one input and give you one and only one output.
You're just restricting the domain.
We're actually restricting the range. So we have all decided together, and this is actually something that's important. There's other functions like this, like inverse trig functions, where we have all decided together that we are going to agree what the range should be. So for the square root function, even though the square root of 9, you could make a convincing argument that the square root of 9 should be negative 3. The math world has said no. We all agree the square root of 9 is positive 3. We're always going to take the positive square root. So here's the kind of two sides of this. If I want to find the square root of 9, that's for sure 3. Versus if I want to solve the equation x squared equal to 9, what do I do to both sides of this equation? Take the square root. Square root of x squared equals the square root of 9. Square root of 9 is only 3. It's not negative 3. It's not plus or minus 3. It's just 3. What's the square root of x squared? Well, you're close. Absolute value of x. So if the absolute value of x equals 3, that means our solutions are that x could be positive 3, or x could be right. It is, but this is why we say that. So this is showing you all the work. So really, if you were solving this, you would never show all this work. I wouldn't. It's a pain. What you would do is say, oh, I know there's a rule for that when you take the square root of both sides, you end up getting x equal to the plus or minus square root of 9. And that's circumventing all this work that's actually happening behind the scenes.
You wouldn't say plus or minus 3.
No, I would. I just didn't want to say that yet. I would totally say plus or minus 3.
So what if x wasn't just absolute value, unless it was a longer expression? Let's say we have a square root of x plus 2 is squared. how would that work?
It'd work the same way. It'd be the opposite value of
It
x
has
plus
to
2.
be the same, but how would the process go? Because wouldn't x be positive and negative depending on the value of x?
It would.
So would you have to specify that?
You would.
So could you do something like that? So for
We
example,
could, but I want to focus us back on what we're doing here because we're getting a little off topic. So let's go ahead and come back around to some limits. And so here's what I want to say about limits in general. If you're finding a limit and you get a 0 over 0, what you really want to do is you want to do some algebra. Maybe some trig algebra like multiply by a conjugate. But the things we've seen is that if you take the limit x approaches a of some function and you get 0 over 0, typically we're going to do some algebra. Meaning you might factor and cancel. Or you might multiply by a conjugate and then factor and cancel. Or you might get a common denominator and then factor and cancel. There's almost always some factoring and canceling. But those are kind of, or you might do some trig stuff. Trig stuff. So if you see a 0 over 0 type of limit, that is your clue to do some algebra, typically. There are a couple of exceptions to that, which we'll eventually get into. But for now, that's what you should be thinking. If I see a 0 over 0 type of limit, I'm going to try and manipulate it in some way to make it simpler so I can factor and cancel some stuff and then plug into what's remaining. All right. Occasionally, though, you're stuck with something not so nice. So sometimes, whoops, paper's all over the place. Sometimes you get 0 over 0 limits and you can't really deal with them. There isn't a nice algebraic method to do it, like the following. Let's say we have the limit x approaches 0 of 10 to the x minus 1 over x, which is definitely a question.
What was the last one on that list?
Trig stuff,
Okay, cool.
which is not very specific, I know. Usually trig stuff meaning like multiply by a conjugate with a trig conjugate.
And that will lead us to like things that we did earlier.
Say that one more time,
And
sorry.
then that will lead us like they did.
Right, exactly. I guess I should point out the other identity that might come up, aside from sine squared theta plus cosine squared theta equal to 1. Oh, there is another one. Oh, yeah, there's definitely. Sorry, I didn't do you wrong. Let me mention real quickly here. I know there's one other trig identity for sure that you're going to need, which is the angle sum identity, sine and or cosine. So I'll remind you all that sine of a plus b is equal to sine of a times cosine of b plus cosine of a times sine of b. That one is definitely going to come up when we talk about the definition of the derivative of sine. And similarly for cosine. I wouldn't say, I don't think you really need to like memorize that one, but you need to know to be aware of it so that when we talk about the derivative of sine or cosine, you're like, oh yeah, I've seen that thing before. I know it's a rule. The other one I wanted to mention was my favorite one, which will come up. I'm not just mentioning this is my favorite. That's my favorite because a student taught me a way that you'll never forget it. 1 plus tangent squared theta equals secant squared theta. Or as my student said once upon a time, I tan and get sexy. Unforgettable. You'll never forget it. Burn it into your brains. You can't forget I tan and get sexy. 1 plus tangent squared theta equals secant squared theta. So now you all two are cursed with knowing that I tan and get sexy. All right. So this limit is a 0 over 0 limit. And there isn't a good algebraic way of manipulating it. I can't factor and cancel this. There's nothing I can really do here. We're kind of stuck with making a list of values to see as x is closer and closer to 0, what this limit gets closer and closer to. So let's make a list. And by make a list, I mean, at some point I pulled out my calculator and made this list of values. So let's start with x, and let's say that f of x is equal to 10 to the x minus 1 over x. So if I plug in x equal to negative 0.1, I get a function value of 2.057 approximately. And if I plug in x equal to negative 0.01, right, which is kind of a pain. So if I was doing actually, so just as kind of a point of interest, if I was actually calculating this and didn't want to keep typing the same like 5, 6 things into my calculator, here's an easier way to do this. I would either use the graphing table in a graphing calculator or use Desmos. And what I would do is I would graph the thing. Y equals, what do I got here? 10, not 10 to the x. Paper's in the way, -1. All divided by x. And then what I would do, if I was smart, remember how to do it, I would here. Yeah, I would grab a table and then just start plugging in my x values that I want to check. So I can plug in x equal to negative 0.1. And get the, oh, why are you so cruel? I have to call you x1. I wanted to grab a table, not, there's a way to like do it from here. Oh, there we go. You click on that, the gear thing, and then you click on the table there. Okay, you gotta be smart. Okay, so negative, if I plug in negative 0.1, it gives me the value I got, which was 2.057 approximately. If I plug in negative 0.01, I get the next value. And you can just keep, right, it's a lot easier than typing things in your calculator over and over and over again. So if you have to like find lots of values for a function, this is an easy way to do it, I think. So plugging in that value, we got 2.276. Plugging in one more negative value, we get, so if we go to negative 0.001, we're getting approximately 2. That looks wrong. Let's plug it in Desmos because I don't believe that value is correct that I've written down. The negative 0.001, 2.2. I see. Yeah, that 9 looks like a 2. 2.299. 9. Okay, and then from the other side, we go to positive 0.0 or positive 0.1. We get approximately 2.589. Positive 0.01, we get approximately 2.329. And positive 0.001, we get 2.305. So we're doing this because we asked, oh, sorry, you can't see what I'm writing, apologies. We're doing this because we were asked what this limit is. So we want to know, as x is closer and closer to 0, what is this function getting closer and closer to? It's not the only way, but it's the only way that we currently have available to us.
So even though this is the only way that's available currently to us, we will not have calculators currently.
Right, but on a homework assignment, you might be asked to do something like this.
On an exam, would it just be more like conceptual to answer? Or like,
So if someone gave you this question on an exam, they would be asking you to do something different, I think. So let me finish off what we're talking about here. So if x is getting closer and closer to 0, what would you all want to maybe guess is the value we're getting close to? Sure, I think 2.3 seems like a reasonable answer. So I would say that this limit as x approaches 0 of 10 to the x minus 1 over x is approximately 2.3. That's not the actual value. The actual value is the natural log of 10, which is close to 2.3. So I actually don't, yeah, it's natural log of 10 is about 2.3. So actually, this limit as x approaches 0 of 10 to the x minus 1 over x is natural log of 10. And we will see that later by, well, much later we can see it by using L'Hopital's rule. We'll actually see it sooner because we can look at it as a limit definition of the derivative. So I saw a couple hands. Well, yes, we could definitely do that. So I feel like we're, again, there is a way of doing this, but the point of this question right now is just to see that sometimes you kind of do have to do this exploration where you're just plugging in numbers and see what you're getting closer and closer to. It doesn't always give you something exactly right, but it gives us an idea of what the limit might be. Later on, after we've talked about the limit definition of the derivative, we can see how that sometimes people like to ask you what a limit is, but what they're really doing is they're disguising it. They're saying, I want you to find this limit, but your job is to really see that that limit is the definition of the derivative. And so that what you're actually going to do is find the derivative and then find it that way. So just for example, let me point out a question like that. We're not going to finish it, but I will tell you, someone could ask you in the future something like the following. Someone could say, I want you to find limit h approaches 0. Now I have to make something up so that it's not too terrible. Sine of pi, sure. Sine of pi over 3 plus h minus sine of pi over 3 all over h. Now, you could totally probably maybe find that one. I got very, very qualitative. Totally probably maybe. But the point is that this is, or we will see later, this looks like the limit definition of the derivative. This looks like the derivative of the sine function at where? Yeah, so this is the derivative of f of x equal to sine of x evaluated at pi over 3, which is much easier to calculate once we know how to find the derivative of sine than it is to actually try and evaluate this limit.
So I can see how this one would cancel out because I just expand the sign.
Mhm.
But for the one that we just did, 10 to the power of x minus 1, I can't see how that would be solved algebraically.
So, well, we can't solve it algebraically. So that's why that one you kind of have to use the fact that it's the definition of the derivative.
But shouldn't the definition of derivative be derived at some point for that?
Well, so so you can find that limit. It requires additional techniques other than just algebraic methods. So we have to use, it actually boils down to using the fact that E is defined as a limit. So you can find that limit. People kind of often are a little hand wavy about it because it's like, so yeah. Let's see, I had one other thing here. Ooh, yeah, okay, so what about the limit x approaches 0 from the right of sine of 1 over x? So this one, you can try to start plugging in values. And depending on how far you go, you might kind of let yourself get convinced that something is not. So if we start plugging in values here, so if I start with, like maybe 0.1, I get a y, and I'm literally just looking at numbers. I'm going to get sine of 1 over 0.1, which is negative 0.54. If I plug in 0.01, I'm getting negative 0.51. Okay, that's looking good so far. It looks like I might be getting close to negative 1/2. Maybe. If I plug in 0.001, I get positive 0.87. Well, that throws that off. If I plug in 0.0001, I get negative 0.31. So what's going on? So this is where I think, especially if you're talking about limits, if you're trying to evaluate a limit, it's really nice to know what the graph of your thing looks like. So if I was trying to figure out what this limit might be, I would probably try graphing it. So if I graph sine of 1 over x and zoom in, getting closer and closer to 0, it's looking pretty bonkers over there. It's looking like it just goes up and down and up and down and up and down, literally forever and ever and ever. So this function, as you get closer and closer to 0 from the right, oscillates between -1 and 1 infinitely. It keeps going back and forth. It never ends. You can always find a point that's close to 0 that gets you back up to 1 or back down to -1 or somewhere in between. So this limit does not exist. Oh, yes, sorry. I do. Yes, of course. Let's brighten that up. And that limit does not exist. Sine of 1 over x oscillates infinitely between -1 and 1 as x approaches 0.
So how do you find out without a calculator? You just have to know
You kind of, so yes, so here's what I would say. There's a couple ways to think about what's going on here. As x is getting closer and closer to 0, 1 over x is getting infinitely large. And if you think about what happens to sine as the inputs get infinitely large, sine just keeps doing this forever and ever and ever out to the end. The other way of doing this is kind of, I don't recommend it, but there is kind of a way of showing, not kind of, there is a way of showing that no matter how close you get to 0, this function can either be up at +1 or down at -1. Here's how it's typically done. If you let x equal, so I'm going to pick things that are closer and closer to 0. I'm going to pick, I don't know what they are. Let me think for a second here. I want pi over 2. I want, so 2 over pi, okay. So I want like 2 over pi, and then 2 over 5 pi, and then 2 over 9 pi. So let me ask you all, would you agree that those numbers are getting smaller? 2 over pi, 2 over 5 pi, 2 over 9 pi, so on, so on, so on. Okay. And then also, I want the other ones, which are 2 over 3 pi, 2 over 7 pi, 2 over 11 pi, and so on and so on. Which are also getting closer and closer to 0, right? So two things. One, I can keep finding numbers that look like this, that are positive and closer to 0. I'm just adding 4 pi in the denominator every time. So 2 over 13 pi, 17 pi, 21 pi, and so on. I can do that forever and always find a positive number closer and closer and closer to 0. And the same thing down here. 2 over 3 pi, 2 over 7 pi, 2 over 11 pi, positive number closer to 0. But now look what happens when I plug any one of these numbers into sine of 1 over x. What is sine of 1 over 2 over pi? It's sine of pi over 2, which is what? Is 1. What's sine of 2 over 5 pi? Sine of 5 pi over 2, which is also 1 because it's on the same spot on the unit circle. All of these, if you flip them over, differ by 4 pi over 2, which is 2 pi, which is 1 revolution on the unit circle. So each of these, when you plug each of these in, sine of any of these is equal to positive 1. On the other hand, these are the ones that end up at the bottom of the unit circle. Sine of any of those, sine of 1 over 2 over 3 pi is sine of 3 pi over 2, which is equal to -1. So the idea here is that I have an infinite number of points that give me a positive 1 value, and I have an infinite number of points that give me a -1 value. And all of these are in between all of these.
like the informal definition of a limit.
The informal definition of a limit, I would say, is that we are looking for what the function is getting close to as x gets close to a particular value.
Trying to see when it's getting.
Actually, let me clarify one small thing. We're looking for the one single value that the function is getting close to as x approaches a particular value.
Pushing anything because it's just infinitely oscillating between a range.
Right, exactly.
So I understand that what you should prove that the function is oscillating, but how do you know that the function doesn't approach any particular value at 0?
Well, because I can do this as close to 0 as you want.
But wouldn't you be able to do the same thing with sine of just x? It wasn't sine of 1 over x.
No, definitely not.
What would be the difference?
Well, because so if I plug in these values into sine over x, I'm going to get sine of smaller and smaller numbers, which are going to get me closer and closer to 0.
But if you could just believe that the x value, because you're
Right, but if you flip the x values, then those values are getting bigger. These aren't approaching 0. Pi over 2 is smaller than 5 pi over 2, it's smaller than 9 pi over 2. So if you flip these all over, you get values that are getting larger and larger and larger and larger.
find the other side.
Right, that's going out towards infinity, not towards 0.
So could we have, like, let's say if we flip it and we have pi over 2, we couldn't minus it by any number that would be less than, that would be greater than 0, but also would be.
So let me say that if you want to find the limit as x approaches 0 of just sine of x, it's just 0. If you just plug it in. Right, going back to our limit roots, right? If you can plug it in, you get a value, you're done. This one here, if you want to think about this one a little bit more in depth, if we start looking at the graph, which we already have up there, but if we start actually graphing it out, so these are in order. That's less than that, that's less than that. That's right. As the denominator gets bigger, the fraction gets smaller. So I have maybe 2 over pi out here, and then I'm not really writing these in any nice, I'm sorry, yeah. These aren't going to be as spaced out as they maybe should be. But the idea is that we're just getting closer and closer to 0. And then when you plug in 2 over pi, you get a value of 1. Then when you plug in 2 over 3 pi, you get a value of -1. 2 over 5 pi, you're back at 1. 2 over 7 pi, you're back at -1, and so on. And I can do this forever, right? I'm never going to run out of values that let me do this. So no matter how close you get to 0, I can keep finding values that go back and forth and back and forth and back and forth and back and forth and back and forth, and it never ends. Because I can always find another value that gets me up to 1 and then back down to -1.
And the fact that you're dividing by 1 lets the values get closer to 0, but never actually reach it.
Right. Yeah. Okay. All right. On the other hand, if we were looking at something that looks similar but is actually quite different, we can do cool stuff. What about the limit as x goes to 0 of x squared times sine of 1? So we just saw the sine of 1 over x oscillates forever and ever and ever and ever when you get closer and closer to 0. But x squared is going to help us deal with that. So this is another example of a problem that's a squeeze theorem problem. So when you're thinking, if someone's saying you might want to use the squeeze theorem, when I hear the word squeeze theorem, the first thing I usually think of, oh, there's probably going to be sine or cosine of something, and I have to set that to be between -1 and 1. That is the first thing you should, it's not the only thing that ever happens with the squeeze theorem, but it is the typical go-to for most people. They're like, oh, squeeze theorem, I'm probably going to have to use the fact that sine of whatever, doesn't matter what's in there, sine of whatever is always between 1 and -1. Yeah.
Are we going to be defining squeeze theorem?
Yeah, we should define the squeeze theorem. Let's do this example and we'll define it. So I might have to look at the definition to actually have it like, I mean, sure. No, yeah, it's, I should not have looked at the definition. So then the whole kind of process with the squeeze theorem is you take this inequality and then you try to make the middle part look like what you are trying to take the limit of. So to do that, I'm going to use multiplication, division, addition, subtraction. I'm just going to multiply everything by what I need to so that it looks like what I want it to be. Meaning I'm just going to multiply everything by x squared. Totally allowed, right? I can, if this is less than that, and you multiply them all by the same thing, you still have the same inequality. Technically, I should say, if you multiply by a negative, you have to change the direction of the inequality, so be careful about that. But we know x squared is always non-negative, so no worries there. So it's definitely true that -1 times x squared is less than or equal to x squared times sine of 1 over x is less than or equal to x squared times 1. And then after you have the thing you want in the middle, the hope is that the limits of the outer parts of the inequality end up being the same. They have to be exactly the same. They can't be a little bit different. They have to be the same. So we're going to say, well, if I take the limit as x approaches 0 of positive x squared, what do I get? Definitely, right? I'm just going to plug in 0 and get 0. And the limit as x approaches 0 of negative x squared is also 0. So then, since the limit of that 0 and the limit of that 0, and that's in between the two things, its limit has to be 0. And we're going to see a picture in just a second here. But we say, by the squeeze theorem, or the sandwich theorem, whichever word you prefer to use, the limit of the middle part has to also be the same. Really, what you can also think of doing is you're really just taking the limit of each part and saying the limit of this is less than or equal to the limit of that is less than or equal to the limit of that. And since the limit of that's 0 and the limit of that's 0, then if you're between 0 and 0, you have to be 0. One sec. So if we look at the graphs, check this out. Here's what we've said. We've said that our graph is below this graph and above this graph. Oops, that was not x equal. That's terrible, James. Our graph is between those two graphs. And so as we move closer and closer and closer to 0, it has to go to 0. And here's what the graph that we're actually looking at is. If we have x squared times sine of 1 over x. Whoops, yeah. Common mistake I make when I do this. So zooming in a little bit, check that out. Our function, x squared sine of 1 over x, is really stuck between those two graphs, right? It has to be under x squared, has to be above negative x squared, and you're just bouncing back and forth and back and forth. You're still oscillating an infinite number of times, but you're also getting smaller as you oscillate. So you're getting closer and closer and closer to that 0 value.
So I'm understanding the individual parts because we just went over the whole, 1 over x thing.
Yes.
This yesterday in lecture, so I understood it in the way that my professor was discussing it, where he was like, imagine if you had like 3 different functions, like g of x, h of x, f of x. So for here, I'm like failing to connect like what we originally did with the x squared, like, oh.
But the arrow is not pointing, that arrow should be pointing to the whole thing.
Okay, so I get that, but then from the original like limit like that we had above, is that like that's x squared times sine of 1 over x?
Correct.
So the bounds that we give from the f of x and the h of x, are those like let's say would those be given in the problem?
Often, yes. So I haven't been textbook. I know there's like I've seen textbook problems before where they're like, you have a function between these other two functions, and the function in the middle is unknown. So like for example, someone could give you an example, and I'm going to try and make something up that actually works. They could be like, we have a function. So suppose that we know that g of x is less than or equal to, let me make something up that's not going to suck, the square root of 4 plus x squared, and bigger than or equal to, oh, I don't know. Sorry, I made up numbers that, let's make this a 9. Let's say, sure, x plus 1. Is that going to work? Yeah, that's going to work. Okay. Let's say the g of x is between those two functions. And they're going to ask us to find the limit x approaches 4 of g of x. Well, this question is screaming squeeze theorem, right? You were given this compound inequality where the thing you're trying to find the limit of is in the middle. To be able to use the squeeze theorem, we have to get that the two outer functions have the same limit. If they don't, we're stuck. You're done, right? You can't use the squeeze theorem. But they end up working out here. So we're going to say, well, okay, the limit as x approaches 4 of x plus 1 is 5. And hopefully, if I've done my math right, the limit as x approaches 4 of the square root of 9 plus 9. I should show more work here. This is 4 plus 1, which is 5. And the limit as x approaches 4 of 4 plus, of the square root of 9 plus x squared, I can just plug it in and get the square root of 9 plus 4 squared, which is the square root of 9 plus 16, which is the square root of 20. Wow, that looks terrible, James. Which is 5. So because the limit of this is 5 and the limit of that's 5, the limit of that has to be 5.
So in the problem that we had previously, I just like my brain blipped for 2 seconds and didn't follow what you were saying. So basically, like the x squared and the negative x squared on either side, those would have been like articulated to us, right? Right.
But I will say they are often not, if you're given something specifically of this format where you have a sine of something or a cosine of something, because of that,
Right.
right? Because we know, or we are expected to know, that sine of whatever or cosine of whatever is always between -1 and 1.
And because we know that, we can apply that into everything.
Right, and then you can say, oh, but I really want x squared times sine of whatever, so I multiply everything by x squared to get the inequality that I actually need. Yes.
So this applies to any function that has a range that's limited, right? So cosine would be the same.
Yeah, so I would say this is very useful for sine and cosine. Other functions not so much. So that's how you see most of your squeeze theorem examples often will have a sine or a cosine.
So is there any other function that has a very limited range that we could use for this? Like common function. Not really.
The only one I can really think of is inverse tangent. The only other function, common function that has a pretty limited range.
And we could do the same.
Yeah, you can do a similar thing.
For some area that x squared times sine of 1 over a. For actually flipping the signs, what would happen if that was absolute value of x? And the signs would be different depending on the value of x. So if we had absolute value of x times sine of 1 over x, and we wanted to find the limit at x approaching 0.
It would still probably be 0. Because that's 0, because you're still essentially saying this sine of 1 over x is still between two things that are getting closer and closer to 0.
But if we was something like just, I'm giving an example, if it was sine of 1 over x plus 1, and we're trying to find.
Then it's a totally different animal. So I know, we'd have to explore that some other time. So,
So would you recommend for, like, obviously I'm a person who's like high school,
Mhm.
so would you recommend everyone just like memorize like all the trigonometric everything? Since like sine, cosine, tangent, they're not like actual numerical values.
right, so sine, cosine, tangent are functions, right?
Yeah,
So like, you definitely, there is an expectation that you know how to find sine of pi over 3, pi over 6, pi over 4, those kinds of values, cosine, tangents as well. Those are things that don't come up all the time, but they come up enough of the time that you need to know.
but like, say, and I genuinely know I had a really bad English teacher and like also over Zoom. So like,
you're right.
I know it's really bad, but like, for example, it's not like I have like a geometric shape or a circle or anything where I'm physically being shown or asked to find theta, for example, or being shown like something on like a unit circle. I'm just being said sine of a random number. So sine is not something that is equivalent to a numerical value, which I can then algebraically, evaluate.
Right, because like, so if you're being asked to find sine of a number, sure, it's something we can find, but if you're looking at like sine of x, then it's a whole different animal.
Yeah.
So when I'm thinking about sine of x, honestly, what I'm picturing in my head is the graph of sine.
Yeah.
That's what I'm thinking when I think of sine of x. I'm like, oh yeah, it's between 1 and -1. So that's kind of where I'm at with it. But as far as like memorizing all the things, I can't recommend that just because like I'm not good at memorizing. I feel like memorizing is not the way to go.
Yeah.
It's more of a building on things, which I know is not like a super helpful answer, but it's kind of the way I want you to hopefully kind of think about it. I feel like I'm just kind of not answering your question at all, but I don't have a good answer. Amina, I mean, I do think it is worth knowing the unit circle, or in whatever way you are able to evaluate trig functions, you should do that. There's like the left hand or right hand trick where you like for sine of like the first, like the angle, right? You can do this thing where you like put down some fingers and like sine of pi over 6 is the square root of 3 over 2. Sine of pi over 4 is the square root of 2 over 2. And sine of pi over 3 is the square root of 1 over 2, which is 1/2. So they got those backwards. I set them all wrong. Sine of pi over 3 is 1/2. So I'm looking at the wrong part. It's not the square root of 3 over 2, it's the 1/2. Sine of pi over 4 is square root of 2 over 2. Sine of pi over 3 is square root of 3 over 2. I've never been good at, obviously I'm not good at that trick, right? I'm totally jet. But there's lots of different ways of knowing how to do sine and cosine. Right, you can draw triangles, you can use the unit circle. The answer is do what works best for you, which I know is again not the best answer, but it is the answer that is true.
So long story short, list of like basic trig identities we should know, and then also how to go between like the different files or whatever. Values.
Yeah, I would say that's a good sum up. Squeeze theorem. We haven't actually stated this. I will also just to point out though, this function, right? Like if we actually looked at the things I just mentioned, just to kind of point out how it kind of like the idea here is you're saying y equals x plus 1, not very exciting. And then y equal to the other one was the square root of 9 plus x squared. And then let's turn these off. Why don't I see my blind? Oh, because I'm zoomed in too far. So there's those functions, right? And they're totally, right? If you get closer and closer to 5, right, if you get closer and closer to 4, both of them are squeezing into a value of 5, right? So that's what's happening. If our function is between those two functions, it has to have a limit of 5 when it approaches 4 as well. Oh, sorry.
Might be a silly question, but my professor at least has been trying to connect everything to some like real world hypothetical explanation of where you would use it. So like he does stuff with like ecological numbers. How would
Okay.
you use this theorem for anything?
That's always the kind of question that I am less good at answering, to be perfectly honest. I'm very much my brain is very much in math for the sake of math. My best, well, not my best, my often answer is because you're going to use it in the next class. But yeah, like where would you actually use the squeeze theorem in real life? I don't know if I can answer that question because I can't think of a time I've ever used it in quote unquote real life. I mean, I use it in real life all the time because I'm teaching it, but it's a good question that doesn't always have a good answer.
This is from 2.2. So what if it's asking you if when limit x of x, f of x minus 8 over x minus 3 equals 3, find f of x, the limit of f of x.
Oh, that's an interesting question. I like that question. So you're saying like the limit as x approaches what? Of what?
And then the equation is f of x minus 8 over x minus 3.
Of x minus a or 8?
8 equals 3. And they want you to find the limit of x.
Cool. So this one we could just plug it in. And so I'm assuming they're saying find the limit as x approaches 6 of f of x. Right? So this actually is not a bad place to mention this. There are some limit rules. There's like a whole list of limit rules that we never actually use. So I'm going to come back to this in just a second, but let me show you one question that'll kind of tell you about the limit rules. So let's say I want to find the limit as x approaches 3, let's make it terrible, 2x cubed minus 7x plus 6 over x squared plus 1. Okay, so if we were going to find that limit, the way a normal human being would do it is just to jam 3 in there. Right, you just plug in 3. And as long as you don't get 0 over 0, you're good to go. So if I plug in 3, I'm going to get 2 times 3 cubed minus 7 times 3 plus 6 over 3 squared plus 1. 3 cubed is 27 times 2 is 54. I get 54 minus 21 plus 6 over 10. I get 60 minus 21 is 39 over 10. So 39 tenths, or if you like decimals, 3.9. Okay. Technically, I just used like 6 different limit rules to do that. I don't want you to ever use them unless you're specifically asked to, because it's just a lot of stuff we're already kind of doing internally, but not actually explicitly writing down. But let me show you, here's the actual long process that we're doing when we do this. So first step, the limit of a quotient is the quotient of the limits. Meaning if I have the limit as x goes to 3 of 2x cubed minus 7x plus 6 over x squared plus 1, it's equal to the limit of the top part over the limit of the bottom part. Sorry, I'm approaching 3, not 6. So the limit is x approaches 3 of 2x cubed minus 7x plus 6 over the limit is x approaches 3 of x squared plus 1. And then we have another rule that says if you have the limit of a sum, it's the sum of the limits. Or the limit of a difference, it's the difference of limits. So I can break this bottom part up into 2 limits. It's the limit as x approaches 3 of x squared plus the limit as x approaches 3 of 1. And then the top part would be the limit as x approaches 3 of 2x cubed minus the limit as x approaches 3 of 7x plus the limit as x approaches 3 of 6. And then we have some rules that say if you have the limit of a constant, it's just the constant. So these two parts will actually be done with their limits. So this is going to be, at the end here, we're going to get plus 6. The bottom here, we're going to get plus 1. There's also a rule that says if you have the limit of x to a power, it is just that number plugged into the power. So the limit as x approaches 3 of x squared is 3 squared. These ones require a little bit more work first. Before we can do these limits, there's another rule that says, oh, if you have the limit of a constant times a function, you can pull the constant out in front of the limit. So this limit of 2x cubed becomes 2 times the limit as x approaches 3 of x cubed. And this minus limit of x approaches 3 to 7x becomes minus 7 times the limit as x approaches 3 of x. But then there's a rule that says, well, it's actually the same rule we already used. If you have the limit as x approaches the number of x to a power, you just plug in that number. So you get 2 times 3 cubed. And then the same deal here. If you have the limit as x approaches 3 of x, you're just going to get 3. Which is the same thing we got before, right? It's just the terrible way of doing it. So the idea is that when you're doing these limits and you're kind of just quote unquote plugging in your value to see what the function ends up getting closer and closer to, what you're really technically kind of doing, even though you're not writing it all down, is you're going through this whole process of being like, oh, limit of a fraction is the fraction of the limits, limit of the sum is the sum of the limits, limit of x to a power is just that number to the power, and limit of a constant times the function, you can pull out the constant. We're kind of doing all those things without actually ever doing them. It's the same kind of way that later on we take like the derivative of something plus something else. We'll just do the derivative of each part individually and then add the results together. So here, back to this one, what we can say using those rules is that this is equal to the limit as x approaches 6 of f of x minus 8 over the limit as x approaches 6 of x minus 3. And that's equal to the limit as x approaches 6 of f of x minus the limit as x approaches 3 of 8 over the limit as x approaches 6 of x minus the limit as x approaches 6 of 3. All right, so now I'm going to ask everybody, what is the limit as x approaches 3 of 8? Everybody? Sure. Okay, all right. What is the limit as x approaches 6 of 3? What is the limit as x approaches 6 of x? Cool. So now we can take this expression, which is the thing we want to find, limit as x approaches 6 of f of x minus 8 all over 3, and then set it equal to 3. And then we should be able to solve for that limit. So if I multiply both sides by 3, I get that my limit as x approaches 6 of f of x minus 8 equals 9. And if I add 8 to both sides, I get 17.
Is there a rule for limit of 1 over x?
As x approaches what?
Let's just say any number because we
As long as, so yes, so I will say there's a whole list of limit rules. They're kind of, they're kind of terrible to write them all down. But so we just mentioned a few of them. Let's, even though I just said they're terrible. Yeah. So there's some limit rules. The limit x approaches a of a sum is equal to the limit as x approaches a of the first thing plus the limit as x approaches a of the second thing. Again, these are limit rules. that we use all the time, but we actually never write down that we're using. Well, every day. We use them all the time, but we often never actually state that we're using them. Sum and I'm gonna be lazy, difference. So the sum of the limit of a sum is the sum of the limits, and the limit of a difference is the difference of the limits. And then I should say this is all with the caveat that each of the limits exists. Right. So this is only we got off track. Yeah.
Well, I suppose that means we can go back to the last one then.
Sure. Yes.
So then, because you multiplied the 3 to both sides, right?
Correct. Yes.
And then you,
And then I stopped there because I said we could add 8 and get 17.
oh, cool.
But I didn't actually write it down because.
Yeah.
So limit of a sum is the sum of okay, and then again, so these are it's assuming that each limit exists, meaning the limit as x approaches a of f of x exists, and the limit as x approaches a of g of x exists. Then we can say that this is equal to that the limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. The limit as x approaches a of a constant times f of x is equal to the constant times the limit as x approaches a of f of x. And kind of the last big one here is limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x over the limit as x approaches a of g of x, provided that the limit of f of g is not 0. Not quite done, but go ahead.
You're going to probably explain that. So that's 1 over f of x.
Right. So we're definitely yes, we're getting there. So then we have the following as well. These ones are going to feel kind of silly, maybe. So limit as x approaches a of x is a. The limit as x approaches a of x to a power is a to that power. Provided that either a is not 0 or the power is not negative. Because you can't have 0 to a negative power because that's division by 0. So, for example, this would take care of your x to the -1 situation. Right? The limit as x approaches a of x to the -1 is just a to the -1, unless a is 0.
So as long as a is not 0,
Just say
just the same thing as 1 over x to the a.
right.
Okay.
It also works for roots. Limit as x approaches a of the nth root of x is the nth root of a, provided that a is greater than 0. So you don't want to be. So I should say that if n is even, a has to be positive. You can't take an even root of a negative number. And then the last couple ones here, it also works for more complicated things. Like if you have the limit as x approaches a of f of x to a power, it's equal to the limit as x approaches a of f of x to that power. Oops, sorry. Basically, limits travel through functions. That's kind of the way I think about it. If you can either do the power first or the limit first. And then you also have true for roots. Limit as x approaches a of the nth root of f of x is equal to the nth root of the limit as x approaches a.
And this last two would be really useful, right?
Right, yeah. So really the more kind of the broader statement is limits of continuous functions, you can kind of move in and out, right? You can do the limit of the inside part first or the limit of broadly first. So like, for example, if I'm trying to find the limit as x approaches 3 of the square root of 9 plus x squared. I'm not actually going to do it. But what I'm thinking of is, oh, well, that limit can move inside. And the limit of the inside part, the limit of 9 plus x squared is just 9 plus 3 squared. And then my overall limit is the square root of that. So we don't typically write this intermediate step, but the intermediate step would be, oh, this is equal to the square root of the limit as x approaches 3 of 9 plus x squared. And then I take that limit and I get 9 plus 3 plus 9. So my limit is the square root of 21. But again, usually what we're just doing most of the time is just plugging it in, right? We're just saying, oh, limit x equals to 3, we'll substitute in 3 for x, and you get something that works, great, you're done. You get something where you're having division by 0, crap, you need to do something else. That's kind of the story. But again, the bigger story is sometimes you apply these rules. Like in the problem you asked me, that's a perfect example of where you actually kind of need to use these rules to really kind of see what's going on. Now, could we have done that problem without using these rules? Sure. We could have just been like, well, I know that I need something minus 8 over 6. Like I could have just plugged in 6 kind of for x and said this minus 8 over 6 minus 3 is 3 and then solved for f of x that way. That would have worked as well, but it's a little less precise. Okay. Oof, never enough time. We didn't even take a break. Sorry, I got too distracted. It's too late now. Someone had asked, and I had meant to say what the squeeze theorem was. So the squeeze theorem says the following. It's really, I mean, we've already kind of said it twice, but here is kind of the official. So if you have the following, if you have that f of x is less than or equal to g of x is less than or equal to h of x, and the limit as x approaches a of f of x is equal to the limit as x approaches a h of x is some limit value, then we must have the limit as x approaches a of g of x is also equal to that limiting value. That's the whole squeeze theorem.
So what it means for f of x to be less than or equal to g of x, it means that for any given x, the output of f of x is always going to be less than or equal to g of x, but it can never surpass.
Correct. Now, really, you can make this a little bit more restrictive and say, at least in the region around the thing you're approaching, you have this inequality. That's all you really actually need.
Would it matter if it didn't have the equal sign? It was f of x is less than g of x is less than h of x, and they were the same.
That's a good question. I feel like you don't have to have it. You can have a strict inequality there, and it'll still work.
Wouldn't it be a contradiction if they're equal and the value is
So no. So for example, here's an example that's super fun. F of x equal to sine of x over x is always for sure is less than or equal, sorry, is not less than or equal to, apologies, is always strictly less than 1. This function never equals 1. Because the only time sine is equal to, so I should point out, right? Sine of 0 equals 1. Sine of 2 pi. Sine of 0 doesn't equal 1. What kind of crazy things am I writing here? Sorry, I was thinking cosine. Sine of pi over 2 equals 1. Sine of 5 pi over 2 equals 1, etc., etc., etc. But if I plug in a value, and 1 is the biggest sine can ever be, right? There's no larger value sine can ever be. So the top is definitely less than or equal to 1, but I'm dividing by x. So unless you happen to be able to plug in 1 and get it to work, it's not going to work. So this function is always less than or equal to 1, but, and here's the crazy part, the limit as x goes to 0 of sine of x over x is equal to 1. The limit of a function can be a value it's not equal to. True. Let's look at another example. Let's look at an easier graphical example. Okay, here's kind of a silly example. Let's say my function was very limited. Let's say it goes from 1 to 7, and it looks like this. It's 1 and it goes like this. I've made up this new function, and it looks like that. And that function, this function, f of x, I know it's not the best function ever. F of x is certainly always less than 6. For sure. But if I look at the limit as x approaches 7 from the left of f of x, that limit is definitely. And here's what I want to remind you of. The limit is not what the function is actually equal to. The limit is what the function is getting really, 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 really close to. Maybe sometimes it equals it, but it doesn't have to. Right? I could draw the same thing except fill in that circle. Right? I could say this is my new function. And g of x has the same limit. The limit as x approaches 7 from the left of g of x is also 6. Because as x gets really, really close to 7, g of x is getting really, really close to 6.
But that makes sense. But going back to the sine function,
Mhm.
we had different kind of conceptual based on the function what you did. So we are saying that sine of x can never be greater than 1.
Right.
And the only value is where it does equal 1, it
Mhm.
does not equal 1 sine of x divided by x, because the division would make it less than 1 because the value is greater than 1 itself.
Yep.
So we are getting 1 and dividing it by some value, and that value, if it's not 1, the graph can't be greater than 1.
Right.
Okay.
Okay.
Any way to know that more like quickly, concept, or do you have to always think your way through
I don't know. That's a good question. I'm not sure of the answer to that question. So. Yeah, I kind of didn't really want to start talking about the not get there. So what should I say right now? I should probably still talk about that. All right, so here's where we're going next time. Oh. Hopefully, the Zoom people can hopefully hear me. I just see that my microphone's off here. I'm sure the computer microphone was probably working. Well, I don't see any chat feed. So hopefully when I look at the video later on, there's volume, otherwise it's not super useful. So here's where we're going next time. We're going to start talking about the precise definition of a limit, also known as delta epsilon proofs. And so what we're going to try and show is the idea is we are going to, in some sense, prove that, for example, the limit as x approaches 3 of 2x plus 1 is equal to 7. And this is where the idea of closeness is going to be really important. Because here's what we're going to try to show. We're going to show, I should say by showing, that we can make the function f of x equal to 2x plus 1 as close to 7 as we want by making x as close to 3 as necessary. I'll remind you, the idea of a limit is that as x is getting closer and closer and closer to 3, this function 2x plus 1 is getting closer and closer and closer to 7. Now, yes, you can also just plug in 3 and get 7, but that's not how we prove a limit is what it is. So, yeah.
Oh, what does it say after by? As close to 7 as we want by
Making x as close to 3 as necessary. Yeah, and then never feel like you can always ask for clarification on my terrible handwriting. always something you should be able to ask. So here's kind of the idea. Paper, more paper. I got 2 minutes. Okay. So, for example, I want to sketch, spell that some way, the portion of f of x equal to 2x plus 1, where the difference between my function and my limit is relatively small. So that's what this says, by the way. This is the difference between our function and our limit. If we're taking the limit as x versus 3. So here's what this looks like graphically, and we'll end it with this. So we want to do a fairly decent job of graphing it. 6, 7, 8, 9, sure. 1, 2, 3. All right. And so this should look like, see, I should get the point 0, 1, and 1, 3, and 2, 5, 3, 7, 4, 9. Okay, so here's my kind of, okay, James. All but one of them, sorry. Oh, but I drew too much. I only wanted the part where the difference between my function and 7 was less than 1. So here's my function, and 1, 2, 3, 4, 5, 6, 7. Here's 7. And I want the difference between my function and 7 to be less than 1. So I only want to go as much as 1 above 7 to almost 8, and 1 below 7 to almost 6. So I really only want this portion of the function. That's the part of the function where the difference between the function and 7 and its limit is less than 1. And now the question is, what are the x values that correspond to this portion? Well, let's see. If if I look at 6 here, if my function is equal to 6, x is equal to 6 minus 1 divided by 2. And if my function is equal to 8, then x is equal to 8 minus 1 divided by 2. So that's kind of the idea, is that we can say, oh, look, to get our function to be within 1 of its limit, we need x to be within 1/2 of what it's approaching. So we need x to be between 5/2 and 7/2. Or written another way, this is kind of the important way, we need the difference between x and the thing it's approaching in absolute value to be less than 1/2.